Hello there, so I'll start off with the introduction to DC shunt motor. A DC shunt motor is a type of self-excited DC motor where the field windings are connected in parallel to the armature winding of the motor. They convert direct current DC from electrical energy into mechanical energy as shown in the video. The most common types rely on the forces produced by induced magnetic fields due to flowing current in the coil. Thus, shunt motors are utilized in applications where a constant speed is required. So the example of applications will be shown later. Now I'll be discussing about the equivalent circuit for shunt DC motor. Shunt is just another name for parallel. The shunt field, this is the shunt field here, is parallel with the armature. This one is the armature. And they are the real starts on the shunt. The shunt is connected to a positive terminal and the negative terminal of the voltage source. Since they are connected in parallel, the armature and the shunt field are exposed to the same voltage supply. Let's now consider to the voltage and current being supplied from the electrical terminal to the motor. The current supplied to the shunt DC motor is split up into two parts, which are IA, the current flowing through the armature, and IL or ISH is the same. IL is the current flowing through the field winding of resistance RSH. And these are the equations for finding the currents. And now, we put this value of armature current, IA, to get the general voltage equation. The EB here refers to the induced back EMF. When the motor is in its running condition, the supply voltage is constant and the shunt field current equation is given by ISH equals to EMF over energy over RSH. Since V and RSH both remains constant, shunt current also remains essentially constant, and the current field is responsible for the generation of flux. Hence, the field flux is directly proportional to the field current ISH. Thus, the field current remains more or less constant, and for this reason, a shunt DC motor is called a constant flux motor. So finally, we will talk about the power flow in a shunt DC motor. And basically, the power supply is power in equals to VT times IL. And these are the equations for calculating field loss and armature loss, the total loss in the DC motor. So that lastly, the developed power is equals to P developed equals to IA times EA. And that's all for the relevant equations about shunt DC motor. Thank you.
The torque speed characteristic of a shunt DC motor is a graph that shows the relationship between the torque produced by the motor and its speed of rotation. The torque speed characteristic of a shunt DC motor is determined by the interaction between the armature winding, which is connected to the load, and the shunt field winding, which is connected in parallel to the armature winding. First, let us have a look on the relevant equation, where the electric torque TE is directly proportional to armature current IA. So when there's a load increase, the current drawn by motor will also increase. With this, it can produces more torques. And this is the graph showing relationship between electric torque and armature current. Next, the second equation will be back EMF is directly proportional to speed, while speed can be equal to this equation. For a DC shunt motor, the back EMF and flux are both constant under normal operating conditions. Therefore, the speed of a shunt motor will remain constant with respect to the armature current as shown by the dotted line. However, when the load is increased, current increase, the back EMF and flux decreases due to the drop in armature resistance and armature reaction respectively. The back EMF decreases somewhat greater than the flux so that the speed of motor decreases slightly with the increases in load. At the end, we substitute IA with electric torque in the equation and we will get the torque speed characteristic graph, which is a straight line pointing downwards. Here I have listed out the comparison of three different graphs as a reference. Typically, the torque speed characteristic of a shunt DC motor can be divided into three regions, where the first is the no-load region. At no load, the shunt field winding provides a constant magnetic field that includes a constant voltage in the armature winding. This results in small torque and a high speed. And the second will be the constant torque. As the load on the motor increase, the armature current also increase, which result in a higher torque being produced. The speed of the motor will decrease as the load increases. The third is the saturation region. If the load of the motor continue to increase, the armature current will reach its maximum value, and the motor will enter the saturation region. In this region, the torque produced by the motor will remain constant, and the speed will continue to decrease.
Application of shunt DC motors is in industrial setting where precise speed control is required. For example, in a machine tool or conveyor belt system, a shunt DC motor can be used to control the speed of the equipment with high accuracy. This is achieved by adjusting the current flowing through the field winding, which in turn changes the magnetic field and the speed of the motor. Another application of shunt DC motors is in electric vehicles. The shunt DC motor's ability to handle high torque loads at low speed make it a good choice for propelling an electric vehicle. The motor can also be used to generate electricity through a regenerative braking, which capture the energy normally lost during braking and store it in the vehicle battery for later use. And the last is shunt DC motor can be used in the fans, blowers, and pumps due to their ability to maintain a constant speed under varying load conditions. This makes them ideal for application where a constant flow rate is required, such as HVAC system or water treatment plant. Shunt DC motor, like all types of motor, have certain disadvantages that must be considered when selecting them for a particular application. One major disadvantage of shunt DC motor is that they have a poor power factor. The power factor is a measure of how efficiently a motor uses electrical power. A low power factor means that a significant amount of the electrical energy supplied to the motor is wasted, leading to higher energy costs. To improve the power factor, additionally equipment such as power factor correction capacitor must be used, which can add the overall cost of the system. Another disadvantage of shunt DC motor is that they have a tendency to overheat. This is because the field winding and the armature winding are connected in parallel, which means that the current flowing through them is the same. This can lead to excessive heating of the field winding, which can cause the damage to the motor or even a fire. To prevent this, proper cooling and ventilation must be provided for the motor. And the last is the shunt DC motor also have a relatively low starting torque compared to other types of DC motor. This means that they have maybe not be suitable for applications that require a high torque at startup, such as in heavy machinery or elevator systems.
So now for the conclusion, maybe just let us look at the practical part. How does the DC shunt motor works?
F1 and A1 are at the same potential, and my A2 and F2 are at the same potential as well. Let's turn this guy on and see how it sounds. Sounds good. It sounds totally different than the series motor.
Basically, that's how it works in practical time. Thank you.